We are starting our lectures after this long break, and this is the first online lecture. We have already completed our studies from the starting of radionuclides, their types, the kind of nuclear radiations, what are radioisotopes, what are its various types, the energy stability, the decay schemes and decay constants. We have also studied the kinetics of radionuclear decay. We have also studied the half-life of various elements. We have studied with carbon dating, carbon-14, uranium, and various elements. And then we move to the detectors, the kind of detectors which are used to detect various kind of radiations. So we use scintillator counters, Geiger-Müller counters, Wilson cloud chambers, and various other detectors. Until mid, our whole syllabus is completed. So after mid, we have like 30% of the syllabus only left. The first part is in these first 2 weeks and followed by the last leg of the syllabus. So today we will start with the radio tracers. And these radio tracers, why we want these radio tracers, what are its uses? Basically, in the last leg of the syllabus, we have two techniques. One is isotopic dilution analysis, and the other one is neutron activation analysis. But before jumping on directly to those techniques, we need to have a little bit of background that how isotopic dilution analysis will be useful and how neutron activation analysis will be useful in analytical chemistry. So the first thing is the radio tracers. The basic idea behind the use of radio tracers is that all the isotopes of a given element will behave the same chemically. For example, radioactive sodium-24 will behave in the same way as stable sodium-23 in a chemical system. So what's the use? Why we want to use it if sodium-24 and sodium-23 are the same? The point is that it is easier to detect a radioactive element like sodium-24 atoms than to detect a non-radioactive element like sodium-23. Using conventional chemical analysis technique, like conventional means like the common analysis technique, not the radionuclear analysis technique, we can detect up to nanogram or microgram of a substance for a non-radioactive stable element like sodium-23. But if we compare it with the radioactive methods, it needs only 10 raised to the power 13 to 10 raised to the power 16 atoms for a conventional method. And for a radioactive element, only one disintegration corresponds to decay of one single atom. So it means if one disintegration happens, it is equivalent to one atom. So the routine radioanalytical technique will allow the detection quantities that are 10 raised to the power 5 times smaller than those needed for a chemical analysis. The high sensitivity of great importance, because it is very sensitive, so it has great importance. Okay, let's see whatever I said, what does it mean? Like we were saying, like, so we were doing it, we were talking about what is the difference between a non-radioactive element and a radioactive element. So we were talking about sodium-23 and we were talking about sodium-24. So on sodium-24, I'm marking as steric, which means it is a radioactive element, and sodium-23 is a non-radioactive stable element. If we look into the abundance, so this is sodium-23 is most abundant because it is naturally occurring in the atmosphere. It is the most abundant, while we have less abundance of radioactive element. But this doesn't really influence our analysis, because as we said that for sodium-24, one disintegration is equivalent to 1 atom. So the quantity required for a radioactive element is really, really less. It means that in lesser quantity and lesser abundance, the results are more as compared to what we were doing with conventional techniques in micrograms or nanograms. So the sensitivity for a radioactive element is more as compared to an abundant non-radioactive elements. That's why we are going for radio tracers. Okay. Now, for example, he says that specificity of pure tritium is approximately 30. Ci means curie, which is the unit of radioactivity per millimole. See, here you are not talking about moles like we talk about in conventional chemistry. So we are talking about millimoles in less quantity. So he says that because the specific activity, the activity of tritium is approximately 30 curie per millimole, which is high. So he says that if we dilute it to 10 is power 12 times, still tritium can be detected or it can be labeled. So what does it mean? It means that you have three radioisotopes. Hydrogen is the abundant, deuterium and tritium. So tritium is sensitive even if we dilute our analyte. Analyte is the substance which is to be determined to many folds. So upon dilution also, the detection is there. So it means if we have one atom of the radioactive element, we will be able to detect it with very much easiness. So that is called as sensitivity. The unique advantages of radio tracer experiments includes their high sensitivity, their simplicity, and small expense. Means because when you don't need a compound in larger concentration, you need a compound in very, very small concentration. So it is more cost effective. It is simpler. Why? Because you don't need a hi-fi system to detect it. You don't need a separate chemical techniques to detect it. Normal analytical techniques are easy, and it is used as same as we mentioned here that sodium 23 and sodium 24 both, they are electronically the same elements. Like the electronic configuration of sodium 23 and sodium 24 is same. The only difference is in their number of neutrons or number of protons. So when we do a chemical reaction, we just don't consider and we just don't look at the number of neutrons and protons. We only look for the electronic configuration, because a radioactive element and a stable element are found in the same position in the periodic table. So it means it behaves same chemically. So when it is behaving same chemically, it means they are going to be the same kind of chemical reactions. In a well-designed experiment, the presence of radio tracer does not affect the system under study, and any analysis is non-destructive. It means that if you design your experiment well, so you will get the desired result irrespective of other radio tracers. They are not going to affect your system. Because what does it mean? It means that the kind of detectors which you are going to use will be very, very specific. Like if you want to detect for alpha particles, that detector will be different. For beta particles, it will be different. For other radiations, it will be different. So the chances of interference will be very, very less. Interference from other species that may be present is not important as compared to conventional method, where interferences may fault the analysis. Because in normal chemical reactions, we think about, okay, like for example, if I want to be really, really specific, so I can, what I can say, okay, like I want to tell you, A reacts with B in a conventional method to form C and D. Suppose the element, yeah, the product of our study is C, but a byproduct is also forming, and it can interfere with the analysis of my product. Like it will affect the percentage yield, and if it has a melting point closer to my product, so it will be of doubt, okay, is it C is it D, or they are both? And simply, and one more thing which is very important, the isolation. When we are going to isolate, so we have to, for conventional method, we have to do like a labor. We have to do various techniques, various methods by which we have to isolate them separately. So the chances of interference in a conventional method is very, very high. But when we go back to the radioactivity method, because it is very, very specific, so we don't need to undergo such interferences. Interferences from other species that may be present is not important, and it does not fault your analysis. So perhaps the most outstanding advantage of the use of radioisotope is to offer a trace dynamic mechanism. For example, what does it mean? What does it mean by a trace dynamic mechanism? Like when we talk about our biological systems and we talk about ion transport. So ion transport means what is transporting in like an ion? Okay, hydrogen ion. So it is a very, very small entity, very small entity. So if you want to check that how it is, what is its mobility, what it is changing, like we say, okay, NAD is converted into NADH2. So these two hydrogens, where it came? It came from an ion transport chain. And from oxidized to reduced states and reduced to oxidized state, these hydrogen ions are constantly moving in and out. For a conventional method, it's impossible to detect them. So biological systems are very, very complex. They are very, very, and the amount of ions are present not in bulk. They are not in kilograms. They are not in grams. They are in smaller quantities. So there, the conventional method has a lot of issues, while the radioactive elements, if we use tritium, its sensitivity is high. Even the sample is dilute, it will still detect the presence. So these methods are very, very important. Okay. One thing it also said in this slide, that what they said, that these methods, the radioactive methods, are non-destructive. What does it means? Non-destructive means it does not destroy the existence of your sample. Like when we go for mass spectrometry, what we do, we say, okay, this is a molecule, so it will lose an electron and it will generate in itself into a molecular ion. So it will lose an electron. At this stage, only one electron is lost, but later it is broken down into fragments. It is fragmented. So when we talk about fragments, it means that it has degraded. It is no longer the same starting molecule which we were doing for analysis. Okay. For radio tracers, this kind of disintegration or fragmentation is not there. The use of term isotopic effect is used to study the rate determining step. So what do you mean by a rate determining step? What is a rate determining step? So there are two kinds of reactions normally. Basically, there are many kinds of reactions, but when we are studying analytical chemistry or general chemistry, we normally say the rate of reaction. So what is the rate of reaction? That how faster your products will form, or it will go back to your reactant if it is a reversible reaction. So we say, okay, if it is very, very fast, so there is a probability that it is difficult to interpret the mechanism of that reaction, to study its kinetic, to study its rate. If it is very, very slow, like 1,000 years or 10,000 years, so for one generation or one scientist, they are difficult to study. But radio tracers found its utility only with those elements which are, only with those isotopic elements, which has a rate which can be determined in a specified period of time. Okay. So the term isotopic effect refers to the influence of a rate of reaction to difference with the masses of isotopes. This effect may create significant problems. Like, okay, there are problems with the radio tracer, but the advantage is this. What can be the advantage? The advantage is this, because we are using the radio tracer in a very, very limited number. The amount is very, very less. So the interference, if it will be created by another isotope, which will be only different in the mass, will be very, very less and very, very minute. So it won't create faults to your result. Okay. Now, how to design a radio tracer experiments? In doing so, we need to assume something. What does it mean? Assume doesn't mean that we will think only in our dreams or thought. It means that these things should be kept in mind before doing anything. Okay, so he says that, like, the first assumption which you see is the radioactive isotopes of a given element behave identically same as a stable isotope of the same element. As I told you before, that isotopic elements and the non-radioactive stable element, they are found exactly in the same place in the periodic table, because when we talk about chemical analysis, we put aside the number of neutrons or protons in the element. We only talk about the electronic configuration. So actually this assumption is not exactly true. He says, how? Like, you are saying that they are identical, but you are saying that this assumption is not true. He says that isotopic effect appears in this thing. How? The only thing which you need to know in this thing is that if you have sodium 23 and you have sodium 24, or if you have hydrogen, the normal element, deuterium, or tritium, the isotopic elements, they will follow the same chemical reaction as their naturally abundant isotope, but because they are heavier in mass, like if you see that sodium 23 and sodium 24, there is a 1 unit difference. If you see hydrogen, deuterium, and tritium, so in deuterium there is a difference of 1 unit, and in tritium there is a difference of 2 units. So we say that it is heavier. It is heavier, so it will undergo the same reaction. But if the rate of reaction of hydrogen is fast, the rate of reaction of deuterium and tritium will be slow because they are heavier. That's why they say that there can be a shift in the rate of the reaction equilibrium. It will undergo the same reaction, but it will be a bit slower as compared to a conventional abundant element. However, in most cases, the isotopic effect does not significantly affect the utility of isotopic method, since the degree of chemical bond stability is directly proportional to the square root of masses. So he says that isotopic effect will be significant only for those elements which have a low atomic weight, like less than 25, like you have hydrogen, you have carbon. So their atomic weight is less than 25. So there you can have isotopic effect in significance, but in all other elements, it has no significance. The isotope of hydrogen present the extreme case, as I told you, like there is deuterium, and deuterium is represented by a D, and tritium is represented by a capital T. Could expect, because the masses difference with hydrogen, one is 2 times heavier and the other one is 3 times heavier. So obviously the relative masses are there. So tritium cannot be employed as a tracer for hydrogen, because the rate of reactions will be very, very slow as compared to that of a normal abundant hydrogen atom. Okay. In case of radioactive carbon 14 and stable carbon 12, there is a 15% difference in mass which affect the outcome of some studies. Like how? uh, it is of like two types. One is intermolecular and the other one is intramolecular. So first type we will discuss, like decarboxylation, means removal of carbon dioxide from the carbonyl group. So he has discussed the malonic acid. So malonic acid has 3 carbon atoms. If for sake of convenience, you can label at 1, 2, and 3 for your convenience. So he says that suppose the 2 carbon atoms are carbon 12, like the normal abundant element, and carbon 14 is the one which is a radioactive element. Here the proteolytic decarboxylation of malonic acid can occur from either end of the molecule and give rise to carbon dioxide and acetic acid. So he says, like, from the left hand side or from the right hand side, Carbon dioxide molecule can be removed and acetic acid can be formed very easily. Consequently, if we talk about the bond strength, uh, then he says that you have different bond strength, like you have carbon 12 and carbon 14. So he says that like carbon 12 and carbon 14 bond, because carbon 14 is heavier in mass as compared to carbon 12, so its bond is relatively more stable. So we would expect that carbon dioxide, which is uh, having eliminated in the reaction, would occur from the carbon 12, and the acetic acid will be enriched with carbon 14 in such case. Okay, let's try and see it in a very particular manner. So you have malonic acid. I'm going to write it in an open reaction. So what he's trying to say, that you have carbon 12, and this one is suppose carbon 14, and I'm going to put a steric on it. So it has two pathways. One pathway is this, that carbon dioxide is getting evolved, and there are chances that you have two kind of products, acetic acid and carbon dioxide. Here you can have acetic acid with carbon 14 and carbon dioxide with 12, or you have acetic acid enriched with carbon 12 and you have carbon dioxide enriched with carbon 14. So he says that if we doesn't consider the mass, like carbon 14 is heavier than carbon 12, so the bond strength of carbon 14 is more. So he says that in this category, if we consider the isotopic effect, what can happen, that we have a more enrichment of acetic acid with carbon 14, and carbon dioxide will be evolved with carbon 12. This is what he's trying to say. So I will go back to this slide again, that he says that the first type is the decarboxylation, is the loss of carbon dioxide from carbonyl group. Malonic acid, here the decarboxylation can occur at the either end of the molecule, either from the right hand side or from the left hand side. But if we consider the bond strength, so he says that owing to the greater mass of carbon 14, we would expect that carbon dioxide, which is eliminating, will be enriched in carbon 12, and acetic acid will be enriched in carbon 14. So can we say, when we go to the malonic acid example, just for our convenience, that it is a competition? Competition in what? Competition in removal of carbon dioxide either for carbon 12 side or either from carbon 14 side. So we have competing reactions in radionuclear chemistry also. Now next move to the second assumption. The second assumption is that radioactivity does not change the chemical and physical properties of an experimental system. Physical properties here means like if you are doing a reaction at 100 degrees centigrade and with some element, probably with radioisotope it will occur at the same temperature, same catalyst, and only the rate of reaction will be lesser, the slower. The amount of activity employed should be restricted to the minimum necessary to permit reasonable counting rates in the sample. So you just need a very less amount of dose, less amount of sample. The possibility of excessive concentration of the trace compound can cause, especially in the biological system, uh, a disturbance in the sensitivities. What does it mean? It means that if you have emitters like alpha particles or beta particles, so when alpha particle leaves, so you have a difference of 4 in above side and 2 in the below side. And when you are talking about beta elimination, say there is a difference of 1 unit. So he says that if you are using your radio tracer in a very large amount, you can have problems if you are dealing with alpha emitters or beta negative emitters. So the idea is, when you are going to set up a radio tracer experiment, you are going to do it with the least quantity which is detectable, and the quantity should be least. So excellent sensitivity can be employed with less amount of your radio tracer with a better magnitude, so you can have a better result in less amount. The possibility of interference due to physiological response of radiations are further minimized. He says, what does it mean? He means that as we know that there is a radiation damage, uh, we are all well aware that yes, these radiations are very, very useful in biochemical processes, in chemistry, in analytical chemistry, but they also have demerits and, you know, biological cells, mutations and disadvantages. So he said that we can cope up to these kind of possibilities by using it into in very, very less quantity, and also for a shorter period of time. We cannot use an alpha radiation or neutron or beta emitters for like 1 hour, for 20 hours, for one day. Like we use, we if we are set up an experiment for 3 days, we cannot keep using those radiations for 3 days. So the time which you need to use this radiation should be very, very short term, because when it will be short term, so the bad effect of radiations will not appear. The radiation damage produced by the decaying of the nuclei uh, atom is usually like you can have a different element than the mother element. What does it mean? You have studied this in your theoretical class that, okay, this is your parent molecule. When it will undergo radioactive decay, it will convert it into a daughter molecule. So the daughter molecule will not be the same always as compared to that of a parent molecule. It will be a new element. So when a new element will come, it will have its foreign species, it will have its because it is new, so everything whatever related to a daughter element will be different as compared to the parent element. So it will always be you can have two kind of products via radioactive decay. One kind of product is which we call as a beta stable product, means that it is of like we can talk about for example, we will talk about wait a second. So we can talk about cobalt, radioactive element, and we can talk about its after its decay by gamma emission, because gamma emission does not cause any change in the mass number and atomic number. So it just converts it into a M radioactive, and M means what? Metastable, means it will lose a bit amount of energy. Energy will be lower as compared to that of the parent. So we have two cases. Like in one cases we have a new element, a daughter nuclei. In other cases it is also a daughter nuclei, but it is of the same mass and everything is same except the energy. So he says that if both the mother and daughter, mother means the parent nuclei, are beta emitters, then you might see an increase in the count rate due to its inability to distinguish between a beta negative particle from the tracer, कि वो tracer से आ रहा है, जो radioactive tracer आपने डाला है, या वो disintegrate करके daughter में convert हो गया and it has emitted a beta radiation. So you can have a little bit of faulty result if you are dealing with a beta emitters, because they causes a change in a little bit of count rate. So this can be minimized if we use radiations in a very, very less quantity, and if we use radio tracer in a very, very less quantity. So lesser quantity means more simple, less interference, more cost effective, and less radiation damage. So it is for every point of view, in every point of view it is the same. Now we talk about the third assumption, and this is particular for a very, very simple biological studies, because whatever we study in chemistry, our main aim is that what we are going to do it in clinical trials in biological system. Like if somebody is suffering from cancer, so how radiations are going to be useful in detection of cancer or in elimination of cancer. So this third assumption is very, very important. So he says that if we produce a radio tracer, the chemical level of the compound given to an organism greatly exceeds the normal physiological or chemical level, the experiment results are open to question. What does this line mean? This line means कि अगर आप रेडियो ट्रेसर को बहुत ज्यादा क्वांटिटी में देंगे, maybe in your biological system that compound does not exist in that high quantity. So what will happen? It will disturb the normal physiological or chemical level. For easy and for sake of understanding, it is said that, I might be wrong, but according to the best of my knowledge, they say that alcohol is produced in the body via fermentation and various biochemical pathway in 27 steps. But if a person start taking an alcohol directly, so what he is doing, he is killing those 27 metabolic pathways, first thing. So he is disturbing the physiological behavior of the body and all the biochemical pathway. And the second most important thing, the amount of alcohol which is produced via biochemical pathway is very, very less. And the amount of alcohol which is taken up by the person is much, much larger in amount. That's why it leads to liver and kidney failures, even heart attacks. So similar analogy can be applied in a radio tracer experiment, that if you are applying a radio tracer and if that amount is lesser in your body and you are adding that radio tracer in a very, very high amount, it means you are disturbing the normal physiological and the chemical level in the body. Then the experimental results are open to question. Open to question means क्या है? Now it has a big question mark कि आपका रिजल्ट रिलायबल है या नहीं है, आपका रिजल्ट ठीक है या नहीं है, ठीक है. So the specific activity of the radio tracer must be high enough, means you have to select that radio tracer जिसकी क्वांटिटी कम हो लेकिन उसकी एक्टिविटी ज्यादा, उसका आउटपुट ज्यादा, उसका रिजल्ट ज्यादा हो, एंड दैट शुड बी एडमिनिस्ट्रेड विद इन द नॉर्मल रेंज, यानी आपको बहुत ज्यादा अमाउंट में से ना डालना पड़े. अब उसे एग्जांपल दी कि फॉर एग्जांपल क्लोरीन 36, you know that the normal radioisotope of chlorine is 35, but it has other also chlorine 36, it has chlorine 34, it has chlorine 37. So because chlorine is very, very adaptable for the biological system, लेकिन वो कहते हैं कि about 100 micro curie per gram of chlorine is, it's the maximum requirement. अगर आप इससे ज्यादा जाते हैं, then you are disturbing your chemical level as well as physiological system. This situation is contrast to the specific activity of carbon 14 in barium carbonate, because carbon 14 activity is 2.2 curie per gram of the carbon. So for it varies. What the example is trying to say, that for every element the specific activity is variable. For one element, maybe less quantity gives more activity, and similarly for other element the less quantity is giving less activity, so you need to add that in more quantity. So in the okay, one more thing I just want to be like, doesn't want to complicate the thing, I want to give it one more, I want to give you one more example so that you are able to understand. Like if we are talking about biological system, and if I talk about a simple amino acid, which are the building block of proteins further. So we say, okay, this amino acid exists in body in suppose less quantity, and I have made this carbon, because this carbon is a chiral carbon. You know what is a chiral carbon, which has 4 different groups attached to one another. And this amino acid I'm introducing as a radio tracer. So how do you know that it is a radio tracer? And you have seen that I have put a steric on carbon, means it is not carbon 12, it is in fact carbon 14. So it is a radio labeled carbon. So when I will insert this molecule into the biological system, maybe in our body, and most probably in our body this exists in a lot of protein molecules, in a lot of enzymes. So what does it mean? It means that we have it in a large in a body in a specific quantity. But if I put this radio tracer in a much more amount, then it exceeds our biological system. So our it will disturb the physiological behavior of our proteins, our enzymes, our vitamins, and it will also result in the faulty experimental results. Okay, so now in the end of today's lecture is not the end, like we are close to the end, that what are the practical considerations which we should be thinking before doing any analysis of radio technique. So the primary factor is the availability of radio tracer. You cannot make a radio tracer just because you need it. So you have to see that, okay, if I want a radio tracer of glycine, an amino acid, so I will see, I will be able to make that in lab in good yields, in purity? Is it available for my country, or do I have to import and this and that? So availability is very important. If it is available, what it will be, what will be the benefit? The benefit will be, it will be less costly, it will be cheap, it will be available, I can do it many times, I can put experiments many times. But if it is not available, then we have to, struggle a lot. So I will say how. He says that a primary factor whether a radioisotope of the element to be traced is available with the proper characteristic, like we should know what is the half-life of that radio tracer, what is its energy, so on and so forth. Okay, for example, we say that if the radioisotopes of oxygen and nitrogen element, so you know that in body there are a lot of amino acids and vitamins and proteins which have oxygen and nitrogen, it's the integral elements and carbon. So we need these elements, and their nucleides are there, they have half-life of 2 to 10 minutes. So we can, half-life is like within a range, we can detect an experiment, we can set up many times. So they are available, they are desirable, their half-life are within a range, so it's good. On the other hand, for some elements like sodium 22, sodium 24, cobalt 57 or cobalt 60, we have to be very, very specific. Okay, what do we need? Similarly, chlorine 36 cannot be readily made with the specific desirable activity. So it means we cannot use chlorine 36 so easily as compared to the other elements. And we have to go for corrections and all things. If possible, uh, the emitted radiation should be easy to detect. What does it mean, easy to detect? Like you have already studied, there are different detectors. So आपने डिटेक्ट करना है इसको, आप इसको, वेट अ सेकेंड, मैं इसको ठीक कर लूं. So you want to detect it, आपने इसे detect करना है. So you have various detectors. So there are separate detectors for alpha particles, there are separate detectors for positron, there are separate detectors for beta emitters, there are separate detectors for gamma radiation. So it means that जो भी आपका radiation emit होगा when your radio tracer will be applied, your equipment should be able to detect it easily. If it has a laborious process of isolation or detection is not very good, so आपका जो experiment setup करना है ये एक बेकार हो जाए. Second factor, that the tagged compound is which is desired should be commercially available or can be synthesized. As I told you, if you go back to this slide, I said, okay, मुझे ये वाला amino acid चाहिए. I need this amino acid. So क्या ये amino acid commercially available है? क्या मैं इसको उस तादाद में दोबारा लैब में सिंथेसाइज कर सकती हूँ? इफ यस, देन इट इज वेरी वेरी प्रैक्टिकल, आप इसे अप्लाई कर सकते हैं, इट इज प्लॉजिबल, यू कैन यूज इट. द नंबर ऑफ लेबल्ड कंपाउंड अवेलेबल इज लार्ज इंडीड, बट द सप्लायर्स वो आपको किस तरह से देते हैं उसको, इज इट अवेलेबल इन योर कंट्री, इज इट अवेलेबल इन द स्टॉक, और यू हैव टू इम्पोर्ट द मॉलिक्यूल. In some cases, however, it's not economically feasible. Like I'm not saying it in a negative term, but Pakistan is a developing country. It's not a fully developed country. So we are financially constrained. We have border constraints. So our elements, if we want to purchase some chemical, we have to take permission, or we have to import it from various countries like USA, like Germany, like Korea, like Japan, like China. So for such things we should need to understand, okay, हमें ये वाला रेडियो ट्रेसर चाहिए, हमें वो सिलेक्ट करना है जो कि हमें इजिली अवेलेबल हो, कम कॉस्ट में अवेलेबल हो, और उसका रिजल्ट भी अच्छा हो. Then the other thing is this: the available specific activity may be too low for the proposed experiment, so you cannot use a radio tracer which has a very very low sensitivity. Low sensitivity is not at all needed, so we need a higher sensitivity experiment. So these are the things which should be kept in mind. Now this is a table. You don't need to memorize the whole table. You can memorize 2 or 3 examples. The idea to show this table is what? The idea to show this table is this, like you see, okay, the first example is tritium. Method of production: R means reactor, C means cyclotron. Cyclotron is the machine, just like a reactor. So वो कहता है कि ट्रीट्रियम जो है इसकी हाफ लाइफ 12.33 ईयर है. अब इसको डिके होने में तकरीबन 12.5 साल है, which is a long time. So you cannot use this tracer, because who will wait for 12 years? It is very very difficult. और जो radiation ये emit करता है वो beta negative करता है with an energy of 0.018 million electron volt. Similarly, if you go for carbon 14, it is used in carbon dating with reactor 5000 साल. The half life is very very much long. ये बेनिफिशियल भी है सेंस में, क्योंकि आपको पता है कि जैसे जो आपके रोमन एम्परर्स थे, किंग 8, किंग 6, किंग 4, किंग 1, उनकी बॉडीज जब मिली फ्रॉम द pyramids and all, so they were identified because it can go up to so long period, like 5730 years. If we look up to sodium with the reactor, this is very very practical. 15 घंटे gamma radiation emit कर रहा है with 31.369 billion electron volt. If we see chlorine, तो तकरीबन chlorine 36 है, 3.5. तो आप वो वाले एलिमेंट सिलेक्ट कर सकते हैं जो कि नॉर्मल आप यूज करें, जैसे कार्बन है याद करने के लिए, जैसे सोडियम है, जैसे क्लोरीन है. सो इस तरह के आप यूज कर सकते हैं अपने उसको मेमोराइज करने के लिए. And the most common, which is used in the biological system, especially when we will study RIA, radio immunoanalysis, we use iodine. रिएक्टर से बन रहा है और 59.4 डेज इसकी हाफ लाइफ है. गैमा रेडिएशन ऑफ 0.035. आप इसे याद कर सकते हैं बिकॉज ये आगे आएगा भी. सिमिलरली यू हैव आयोडीन एक 125 है, देन देयर इज अनदर आइसोटोप आयोडीन 131. आर मींस रिएक्टर है, 8.2 डेज है. बीटा नेगेटिव 0.06 मिलियन इलेक्ट्रॉन वोल्ट एंड गैमा रेडिएशन इमिटर है. तो आपके पास ऐसा डिटेक्टर होना चाहिए जो बीटा इमिटर को भी डिटेक्ट कर सके और जो गैमा रेडिएशन को भी डिटेक्ट कर सके. सिमिलरली यू कैन मेमोराइज थेलियम बिकॉज इट इज आल्सो यूज. और आपको पता है थेलियम के सेंटिलेटर्स भी अवेलेबल है. ये साइक्लोट्रॉन प्रोडक्ट है, 72.94 आवर्स है गैमा रेडिएशन इसकी. लेड आप याद कर सकते हैं, 22.3 years है. बीटा नेगेटिव पार्टिकल इमिट करता है, 2 किस्म के, एक की एनर्जी 0.01 है, दूसरे की 0.064. नाउ why we are the last slides of today's lecture, why we are using this, what is the application. We talked about so much that okay, this is the reactor, this is what we are doing, this we should do, we should select these kind of reactors. So where we are going to use it, the idea of everything is how we are going to utilize it. So radioisotopes have found wide use in chemistry because of the distinctive qualities. The first quality is like their precision, their detection. They can be measured. They can be measured in minute quantities. They are good analytical tool. How? Like you don't need a very state of the art equipment or technique for detection of this. So you can use common analytical tool like co-precipitation, solvent extraction, chromatographic technique, ion exchange methods, surface absorption. The mechanism will be same because the electronic configuration is same. So your mechanism can be same. Your structural conformation, we will discuss this in coming lectures in detail. At present, there are up to 200 radioisotopes which are available in regular basis, and they are produced artificially also. Radioactive methods are simple, they are reliable. What does it means by reliable? कि अगर आपने एक experiment, you have placed experiment once, and if you are going to place that experiment after 2 days, it is going to give the same result almost. So it is the only mean by which you solve a definite chemical problem with easiness. And you just need a trace amount. That's why we are constantly using the word radiotracers, radiotracers, and radiotracers. The isotope found useful as a tracer has half-life between few hours and to few thousand years. ये आपने टेबल में भी देखा है. Nuclei which are very short-lived or very long life are not useful as a tracer. क्योंकि जो बहुत शॉर्ट लिव्ड होंगे, शॉर्ट लिव का मतलब है जिनका डिके पीरियड फर्स्ट कर ले 1 मिनट है, हाफ मिनट है, इट इज वेरी डिफिकल्ट टू डिटेक्ट बिकॉज दे एज सून एज दे विल बी अप्लाइड दे विल डिसअपीयर. और वो वाले रेट जो कि बहुत ज्यादा जिनका डिके पीरियड बिलियंस ऑफ इयर्स पे है, यू कैन नॉट डिकेट बिकॉज अब तब तक यू वोंट बी अलाइव टू सी द रिजल्ट. रेडियो आइसोटोप्स may be prepared artificially by bombarding with a nuclear particle. ये आप पढ़ेंगे आगे न्यूट्रॉन एक्टिवेशन एनालिसिस के अंदर, यूरेनियम और उसके अंदर. So you need a cyclotron or a nuclear reactor for it. If the proportion of the isotope is increased by an enrichment process, the element is said to be labeled. If such element is incorporated, this is similarly said to be labeled. For example, what does it mean? In the first slide, we studied, okay, there is sodium 23 and its labeled element is sodium 24. Here we are talking about only one element. But he says that if you label one element in a compound, it will label the whole compound. Like I told you that what we studied, an amino acid. So it is CH3, it is hydrogen, carboxylic group, and NH2 group. So if I label this carbon as carbon 14, there are 4 groups which are attached to it. Hydrogen is attached to it, carboxylic group is attached to it, amino group and methyl group. All are attached to this labeled carbon. So if I will label this central carbon, I will label the whole molecule. So we can have a separate elements as label element like sodium 23 and sodium 24, and we can have a labeled whole molecule also. So he says, suppose that an atom of a particular isotope per 100 atom of the element, the normal abundance will be A atom percent. Because why we are using the term percent? Because we are talking about 100, हमने 100 ले लिया, and that would be 100 minus A. In case the abundance of isotope is raised to B, means you have increased the isotopic abundance, it means you labeled it, then the difference will be B minus A. So आप उसको लेबल करके enrich कर सकते हैं, आप उसे change कर सकते हैं. There are a number of different ways by which radioisotopes can be useful. Analytical techniques are dependent upon the fact that small amount of radioisotopes are conveniently determined. So it is time and again been told, okay, less amount of activity, less amount of radiotracer, give good activity, give less interference, give less safety radiation hazards. So tracer studies may be ascribed as isotopic incorporation and isotopic exchange studies. In isotopic incorporation method, one of the reactant is labeled, I have told you before. And bond making on bond breaking जो भी take place करती है, we will investigate this. ये जो point है, this जो last आपका जो option आ रही है, this option, that how you are going to investigate the bond making and the bond breaking process, this we will discuss in detail in the coming lectures. And then the isotopic incorporation leads to valuable information about the reaction intermediates. जैसे अभी आप अगर पीछे जाएं, if we go back to the example जो अभी हमने की melanic acid की, यहाँ पर आपको the reaction of the use of labeling isotope is giving you an information that the decarboxylation will occur either from carbon 12 or it will occur from either carbon 14. किसी एक से भी हो सकती है. So it is giving you an insight. Conclusions can be drawn about the overall mechanism from the extent of which isotopic exchange undergoes. Isotopes having shorter half-life are associated with high activity. Small quantity of isotopes are added so that no interference is expected. A labeled molecule follows the identical chemistry as unlabeled molecule. Sampling and counting process is easily. Majority of applications pertinent to liquid extractions and ion exchange chromatography. So agar aap liquid extraction kar rahe, solvent extraction kar rahe, you can understand about the dissociation constant, the distribution coefficient between an organic phase and the aqueous phase for a radio tracer. Similarly, as you are doing it for a non-radioactive element. So you can calculate the distribution ratio, the partition coefficient, the formation constant of metal complexes and other related diseases. So this is what our uh, project was about. And